So now that we're done with the basic operations of union, complement, intersection, difference, symmetric difference, and Cartesian product, we're going to move on to more complicated things you can do with sets. And these are going to involve proofs, which might scare some people, but proofs are the backbone of set theory and pretty much all mathematics. So before we do that, we're going to introduce two more operations, cardinality and power sets. We're going to start with cardinality because cardinality is so easy. I think we're going to get it done in like a minute. And then power sets are actually pretty difficult for people to understand. So that's why we're starting off with cardinality. So given a set, it actually is any set, but I'm going to call it S, and then we're going to say 1, 2, and 3. So given our set S, we define the cardinality of a set, and the way you do it is like this. It's like the absolute value of S. We define the cardinality to be the number of things inside of S. So in this case, there's 1, there's 2, there's 3. So there's 3 items inside of S. So the cardinality of S is 3. If we had another set, say for example A, that was 1, 2. The cardinality of A, there are 2 things inside of it, so the cardinality is 2. What is the cardinality of the empty set? Well, there's nothing inside of the empty set, so there are no items inside of the empty set, so the cardinality is 0. What's the cardinality of the real numbers? Well, there gets into some questions about like types of infinity and stuff like that, but there's infinite real numbers, so we're just going to put the cardinality is infinite. That's it. Cardinality is you just count how many things are inside of a set, and you just put that number, and that's the cardinality. Now we're going to move on to power sets. Okay, so now we have the power set. Now the power set is another operation that can be performed on sets, and it's denoted by this like cursive P. It might look fancy, like I overdid it, but it actually is like that fancy when it's written out. And the power set of P is a set that contains all possible subsets of the set we're given. Now, first off, you probably didn't even realize that we were allowed to have sets of sets. I'm not sure if I said that earlier, but you can. You can have sets of sets. Sets are things, right? So you can include them inside of a set because a set is just a collection of things. So this is a set of sets, and it's all possible subsets. So let's start writing out some subsets of S, right? Well, one subset of S is just nothing, the empty set, right? The empty set is a subset of everything, right? So the empty set is in fact a subset, so that goes in here. Well, there's the subset 1. There's the subset 2. 3. So these are all the single element subsets. And then let's write out some double element subsets. Well, there's 1, 2. There's 1, 3. There's 2, 3. Right, so these are all the 2 element subsets. And you might be thinking right now that, oh, well, these are all the possible subsets we can have, that like subsets of S. Well, there's one more that we're missing. We're missing the set S itself, because every subset is a subset of itself, by definition of subset. And that's what the power set is. The power set, again, it's the set of all possible subsets. So you just list them all out like this. So in this case, our power set, we have 8 subsets for our set S. And this stuff grows. This stuff grows fast, depending on like how many items you have inside of our set S. And that is actually what the topic of our next video is going to be, proving how fast does the power set grow, and how many elements are inside of a power set? And with that, that's the end of the video.